this video, we are going to talk about key and certificate handling in the DataPower. I created this video in two parts. Part one, where I intend to provide you theoretical introduction necessary to understand key handling in the DataPower, and part two, where we jump onto the DataPower interface and will experience how the key and certificate handling takes place in the DataPower. If you are already aware about the concepts of cryptography, public key, private key, and symmetric keys, feel free to skip this. This is an intro necessary to understand the concept of key and certificate handling in the DataPower. So let's get started. The field of cryptography essentially revolves around three actors: sender, receiver, and eavesdropper. Sender is the person sends the message. Receiver is the person who is intended recipient of that message. And eavesdropper is somebody who is assumed to have full access on the communication medium, and it is assumed that the eavesdropper can get a copy of every message which is passing between sender and the receiver. There are two fundamental problems in cryptography. One, how to send a private message between sender and receiver. And second, how a message can be sent between sender and receiver in such a way that receiver can understand that it indeed came from sender. This calls for, or this is called, message integrity. Message privacy is all about having a private communication. So message privacy says that sender can send a message to a receiver which only receiver can understand. Even if the eavesdropper gets a message, a copy of that message, the message must be incomprehensible for the eavesdropper. Naturally, you can see that if sender says, "Let's have a dinner tonight," in plain text, a receiver can understand it, yes, but so can eavesdropper. So this is not a private message. You can see by yourself that the message privacy calls for some kind of message transformation. This message transformation is supposed to convert the message, for example, "Let's have a dinner tonight," into something unintelligible, something gibberish. Now, there must be a function, a mathematical function doing the same. And that's what is referred as f1xy on the top left corner. We'll talk about the key in a moment. As you can see that the function transforms a clear text, "Let's have a dinner tonight," to something which looks gibberish, ax something, which you can see here. At the other end, this gibberish goes. Of course, at the other end, we need to have a mechanism where we can convert this gibberish back into clear text, like "Let's have a dinner tonight." So we need another mathematical function for that. The first function, which translates clear text into gibberish, is called encryption function. The process is called encryption. That's its name. The second one, where we convert gibberish back into the clear text, that function is called decryption function. Process is called decryption. Now, it may seem like if we keep the function secret, for example, if two actors, sender and receiver, if they keep these functions secret, they can communicate with each other. Well and good. But it turns out that keeping the function secret may not be a good idea at all. So you essentially, practically, you cannot keep these functions f1 and f2 secret. Okay? So if these functions cannot be kept secret, then these functions are known to eavesdropper as well. And if sender sends a message to the receiver, eavesdropper can get a copy of it. Using the function, it can it can decrypt that message, and it can get a clear text copy of that message. Message privacy is thwarted. Well, it turns out that the function should have something which only the sender and receiver possesses. It's our function. F1 and F2 are our function. We can make it the way we want. So instead of accepting one parameter, let's make it accept two parameters. The second parameter is a number, a text, any data that we label as key. And we say that key is such a number, such a piece of information which is only known to sender and receiver. So now we have a function which is known by everyone, sender, receiver, and eavesdropper, but we have something called key which is known only to sender and receiver. Now, in the process of encryption, apart from the regular clear text, this key is fed as an input and we get an output. Now, this output can only be converted into clear text if we have the right key. And the right key is with the sender and receiver. So even if the eavesdropper has a knowledge of function, even if it can get a copy of every message transmitting between sender and receiver, since it doesn't have the key, it will not be able to perform encryption and decryption process that achieves the message privacy. So you will see that every type of scenario where encryption and decryption is involved, there you will have to generate a pair of keys. And why? Because the pair of keys are prominent. Function remains the same. You have same function, RSA, Diffie, Hellman. These functions remain same every scenario. But the key is something which is unique between the sender and receiver. That's why whenever you have any kind of encryption decryption scenario, you always start with generating a pair of keys. Why pair? Because one should reside with a sender, another one should reside with a receiver. So this solves the message privacy problem. But then the next problem. A sender sent a message to a receiver. Eavesdropper is there. It can trap the message, it can alter it, and it can send it to receiver. And it might trick receiver believing that it has came to a genuine sender. So this is a problem which calls for a solution which is called message integrity. A message integrity means a receiver can prove that the message has actually come from sender. And not surprisingly, this is something which is carried out or solved using something called a digital signature. We do it every day in our life, and the inspiration has come from our everyday life. Imagine days where computers were not there, and when we used to do the banking, we had a bank check where we used to put our signature, and then we send it to the bank. The bank would verify the signature, and here you have the fund transfer. In a similar way, sender should be able to put his signature on the digital information, and this signature is called digital signature. Not surprisingly, again, it's called digital signature. Now, the digital signature is something which must be created using something which sender possesses uniquely. Otherwise, the signature would not work. And it turns out that the solution for message integrity is also in what you call keys. So we have a function. In digital signature world, we have a function. The function would take message as an input, and the function would generate a digital signature. Okay, fine. It can do that. But for that, it needs another parameter. The another parameter is called key. This key is unique for every person who generates the digital signature. That's why you see that whenever you have to generate a digital signature, you always talk about something called private key. This is the key that you will feed as an input to this function, and this will generate or this will come into the digital signature of what is created out of that message. Now, the algorithm of creating digital signature, etc., is out of the current discussion. But in simple words, I tried to explain how the digital signature is created and why there is a need for a key. Now, the world of cryptography is actually divided in two parts. One is called symmetric key cryptography. Another one is called asymmetric key cryptography. Symmetric key cryptography is characterized by the fact that sender and receiver uses exactly same key for both encryption and decryption. It is fast in nature. You can encrypt or decrypt megabytes of data in a matter of seconds. However, core problem in this is how to establish keys between sender and receiver when they are far apart in a secure manner. That's a challenge in symmetric cryptography. However, symmetric cryptography is very fast in nature, and it utilizes, or it is characterized by the fact that sender and receiver uses the exactly same key for both encryption and decryption. Remember that in symmetric cryptography, the keys are called secret keys. Then there is another word. It is called asymmetric cryptography. This is characterized by the fact that sender and receiver uses different but related keys. These keys are of such nature that knowing one key, it is computationally infeasible to derive the second key out of that. Also, materials which are encrypted using one key can only be decrypted using the second key. Meaning, if you use a key to encrypt a text, you cannot use the same key to decrypt the text. It can only be decrypted using the second key. It is comparatively extremely slow compared to symmetric cryptography in such a way that even if you have to encrypt one single page of data with it, it might take several minutes to hours to encrypt that. As you can see, asymmetric key is very slow to an extent that it cannot be used for any practical communication in real world. So the idea is that any practical scheme that utilizes a secure communication, that aims to achieve a secure communication, utilizes best out of both worlds. For example, the SSL TLS scheme utilizes both asymmetric key and symmetric key cryptography. Both have their own advantages and both have their own weaknesses. So the SSL TLS scheme carefully avoids the weaknesses of these schemes and utilizes the strength of both of them. That is what cryptography is all about. The summary section is pretty much what I mentioned. You have to remember that symmetric cryptography is characterized by the fact that both sender and receiver have the same key, and asymmetric key, they will have essentially different keys. Now, these keys, which are different for asymmetric cryptography, they are arbitrarily labeled as public key and private key, which means that when you think about deploying asymmetric cryptography, you'll generate a pair of keys. One of the keys you arbitrarily label as private key. Another one we will label as a public key. And the one that you label as a public key, you can send it across or you can publish it to the world. You need not have to worry about whether it is received by the intended recipient or it is received by the intruder. It doesn't matter. Okay, as long as you are in the possession of the private key, the asymmetric cryptography will work just fine. In symmetric cryptography, you generate one single key. This key is called your secret key, and this key is the one using which both encryption and decryption happens. So that is about both symmetric and asymmetric key cryptography. That's the end of it. See you in part 2, where we jump onto the DataPower interface and we will see how DataPower supports both asymmetric cryptography and symmetric cryptography. Thank you.